Namaste. Today we're going to continue looking at related rates problems, and specifically we're going to look at related rates problems that involve trigonometry of some sort. We'll go through one example that has two parts in this video, and then you will have a couple of example videos to take a look at to get a wide variety of examples and get a little bit of practice. So let's take a look at this first problem. All right, let's read it together. A television camera is positioned 4,000 feet from the base of a rocket launching pad. The angle of elevation of the camera has to change at the correct rate in order to keep the rocket in sight. Also, the mechanism for focusing the camera has to take into account the increasing distance from the camera to the rising rocket. Let's assume the rocket rises vertically and its speed is 600 feet per second when it has risen 3,000 feet. We've got two questions. How fast is the distance from the television camera to the rocket changing at that moment? And then if the television camera is always kept aimed at the rocket, how fast is the camera's angle of elevation changing at that same moment? We're going to tackle these problems one at a time. So we're going to start with the first part. How fast is the distance from the television camera to the rocket changing at that moment? We are going to want a diagram for this, so let me draw a quick one. All right, so here's my crappy drawing because I'm not an artist. I've got the little camera down here. It doesn't even look like a camera, but there we are. And then a little rocket up here. And so we know that it is ascending vertically, so this is going to be a right angle. So we have a right triangle, and we need to label the different sides. Now, we know that the camera is positioned 4,000 feet from the base, so we know that the lower length is going to be 4,000. That's not something that changes. That is a constant, and so we can write it as a constant. Now, the height, of course, is changing as a function of time, so we can write that as y, remembering that y is a function of time. And then, of course, that means that this distance is also changing. Let's call that d. That is the distance. And remember, we're asked how fast is the distance from the television camera to the rocket changing at that moment. So what we want is dd over dt. So we need some sort of relationship between distance and then also the height, because we are given dy over dt. We're told, at least at that moment, the rocket's speed is 600 feet per second. So we need an equation that relates d and y so that we can use implicit differentiation and look at their rates of change. Now, this is a right triangle, so you're probably already thinking Pythagorean theorem. If so, that is great. We've got 4,000 squared plus y squared equals d squared. And we want to differentiate both sides with respect to time. So d over dt. I'm going to skip a step. I don't want to write out d over dt of the left-hand side equals d over dt of the right-hand side. Let's just go through this a little bit more quickly. We're going to differentiate both sides with respect to t. The derivative of a constant is 0. And then the derivative of y squared is going to be 2y, but then times dy over dt. And then on the right-hand side, the derivative of d squared is 2d times dd over dt. All right, we can divide both sides by 2 to simplify things. So y times dy over dt equals d times dd over dt. And then we can substitute in the values that we need here. We know that at this moment, the rocket has risen 3,000 feet. So that means y is 3,000. So we've got 3,000 times dy over dt. Well, we're told the rocket is rising at a speed of 600 feet per second at that moment. So that's going to be 600. Then on the right-hand side, we need to know d. Now, at that point in time, we have, I'm going to draw a really bad sketch of this, but at that moment, we know we've got 4,000 for the base. We said that y was 3,000, and so we need to figure out what that distance is. We can use the Pythagorean theorem, but there is a shortcut if you know your right triangles. There's such a thing as a 3, 4, 5 triangle, and this is going to be a 3,000, 4,000, 5,000 triangle. If you don't already know that, go through and use the Pythagorean theorem on your own. Make sure you can figure out that's 5,000, but once we have that, that's going to be 5,000 times dd over dt. And then we need to divide by 5,000 to get that derivative by itself. So we've got 3,000 times 600 over 5,000. Now we can reduce quite a bit. The easiest way, I think, is to divide 3,000 and 5,000 by 1,000, and that basically cancels out 3 of those zeros. Can't really cancel zeros, but it gets rid of them because it reduces to 3/5. So then we have 3 times 600 over 5. So that's 1,800 over 5. And when we divide 1,800 by 5, we get 360. And if we remind ourselves what that is, it's how fast the distance is changing. And the speeds here are in feet per second. So that distance is changing at a speed of 360 feet per second. That is our part A. Now let's move on to part B. This is the part where we're going to have a little bit of trigonometry. Part B asks, if the television's camera is always kept aimed at the rocket, how fast is the camera's angle of elevation changing at that moment? Well, the angle of elevation, I'm going to call it theta, is the angle between the ground and the rocket from the point of view of the camera. It's the angle of the triangle at the camera. So that is theta. And we want to know what d theta over dt is. And specifically, we want to relate this to dy over dt because that's a rate of change we have. So we need some sort of a relationship between y and theta. And we don't want to include d because that's going to complicate things. So it'd be really nice to involve 4,000. And if we want to do that, then we can see the relationship that's going to work out nicely as tangent. Specifically, tangent theta is equal to y over 4,000. So once we have that, we can differentiate with respect to t. The derivative of tangent theta is, do you remember? Secant squared theta. But then we have to multiply by d theta over dt because theta is a function of time. Remember that angle is changing as time moves on. So that's our left-hand side. The right-hand side, the derivative of y over 4,000 is just 1 over 4,000 and then times dy over dt. So at this point, we just have to substitute in the different values that we have. On the right-hand side, we know dy over dt is 600 feet per second. It's the same as it was in the other problem. So the right-hand side is going to be 1/4000th times 600. D theta over dt is what we're solving for, so we're going to leave that on its own. And then we're going to need secant squared of theta. Well, first we need secant of theta. So if we go to the drawing that I made down here in the bottom, that is what is going on at that very moment. Now we know secant is 1 over cosine. Cosine of this angle would be 4,000 over 5,000, or 4/5. That means secant is the reciprocal of that, which is 5/4. And so this is going to be 5/4 5/4 squared on the left-hand side. Now, 5/4 squared is 25/16 times d theta over dt equals, this is the same on the right as 600 over 4,000. We can divide those both by 100 pretty easily, and that gives us, what, 6 over 40? But we can reduce that even more. If we reduce it by 2, that gives us 3/20. So this is going to be 3/20. And then to get d theta over dt alone, we just multiply by the reciprocal of 25/16, which is 16/20. So that's going to be 3/20 times, 16/25, not 20ths. And then let's see, 3 times 16. Actually, let's do some quick cross-canceling. 16 and 20 are both divisible by 4. That reduces to 4/5. Makes life a little bit easier. 3 times 4 is 12. 5 times 25 is 125. And so we have 12 over 125. And if we wanted to use a calculator to get a decimal version of that, we end up with 0.096. Now, we have to be careful here because this is the rate of change of an angle. And when we're dealing with angles, at least with trigonometry and calculus, we use radians. And since it's the rate of change of the angle with respect to time, that's going to be radians per second. So that camera angle has to be increasing at that moment at a speed of 0.096 radians per second. If it's going too quickly or too slowly, then the rocket is going to go out of frame. Now, I know that some students have weaker trigonometry backgrounds than others. So if that's you, I want to really encourage you to go through some example problems, really get comfortable with this, because when you're struggling with something, the best way to counter that is to really dig in and get extra practice.